we'll be reviewing today are continuity, buoyancy, specific gravity, and Bernoulli's principle. Our first topic is continuity. The equation for continuity is A1 V1 equals A2 V2. V is velocity and A is area. This describes the relationship between mass and flow rate. The larger an area of a tube, the slower the velocity of the fluid moving the tube. But if you decrease the area, the velocity increases, as stated by the relationship between the two variables in this equation. Our next main idea is buoyancy. Buoyancy is based off of an idea by Archimedes. His principle states that the buoyant force acting upwards on an object while it's in a liquid is equal to the weight of the water displaced. Here we have a free body diagram of an ice cube in water. The forces acting on this ice cube are the buoyant force, upwards, the force of gravity, downwards, and the atmospheric pressure. Our equation for buoyancy is the density of the fluid times the acceleration of gravity times the volume of the fluid displaced, or the volume of the object in the fluid. Density equals mass divided by volume. An easy way to remember this is dmv, because most of you will recognize density as d, even though in our equations it's represented by rho, the Greek letter. Our next topic is specific gravity. Specific gravity is defined as the density of an object divided by the density of water, which is 1,000 kilograms per meters cubed. The specific gravity of an object can tell you how much of the object will be submerged in water. An example of how to use specific gravity is finding how much of an iceberg would be submerged below water. The density of ice is 920 kilograms per meters cubed, and the density of water is 1,000 kilograms per meter cubed. If you put these two densities over each other and divide them, the units cancel out because specific gravity is simply a ratio. If you multiply this number by 100, you can solve for how much of the iceberg would be submerged underwater, 92%. Our last concept is Bernoulli's equation. This equation represents the phenomenon that happens when the pressure in an area of a tube decreases. When the pressure decreases, the area of the tube also decreases, allowing the velocity to increase as it goes through the narrower area of the tube. The equation for Bernoulli's effect demonstrates the law of conservation of energy for fluids. Our first variable is the pressure of the fluid. Our second group of variables represents the kinetic energy present in the fluid. As you may remember, the formula for kinetic energy is 1/2 mv squared. So in our Bernoulli equation, this is represented by 1/2 times the rho of the liquid times the velocity of the liquid squared. Our last variable group on either side of the equation represents the potential energy of the liquid. The potential energy is represented by the rho of the liquid times the acceleration of gravity times the height of the liquid. I like to think of Bernoulli's effect as the straw effect. Some of you may have noticed that when drinking through a straw, it collapses a bit. This is due to the lowered pressure as the velocity of the fluid you're drinking increases through the straw. Aside from drawing liquid up through tubes in perfume bottles and in straws, Bernoulli's effect is also useful in aerodynamics. When flying a plane, the air goes faster over the top of the wing than it does the bottom, providing a lift effect. The pressure is reduced on top of the wing. This helps keep the plane in the air. Bernoulli's effect also explains why this works. As the air moves around the curves on the ball, the pressure is reduced and the velocity increases, therefore forcing the ping pong ball to stay inside the airflow, allowing it to seem like it's levitating.